Okay, suppose that 4 teachers and 6 students volunteered to be on a committee. How many 6-member committees does the principal have to choose from if she wants the same number of students and teachers? So, with a 6-member committee and equal numbers of students and teachers, that of course implies we need 3 teachers and 3 students. So we have to ask ourselves, how can we select 3 teachers from a group of 4 teachers and 3 students from a group of 6 students? And I'm assuming order does not matter here because, in my opinion, you're either on the committee or you're not on the committee, and the order in which you are chosen to serve on the committee, at least as of right now, does not seem to matter. So that means we're going to be using combinations. So how many ways can we choose? We can use that word now. Carefully. We can choose 3 teachers from a group of 4. So, of course, when you hear choose, that means combination. And then once we choose our teachers, we also have to make sure we're not finished with our selection process. So we have to multiply and use the fundamental counting principle by the number of ways we can choose 3 students from the group of 6. Of course, that's 6 choose 3, and that would give us 4 times 20, which is equal to 80. So the principal has 80 possible committees that she can choose from. Okay, to make sure we're really clear on why the fundamental counting principle must be applied here, let's assign the last 4 letters of the alphabet. They'll represent the 4 teachers, and the first 6 letters of the alphabet to represent the 6 students. And if we systematically go through W, X, Y, and Z and list exactly 3 letters, where order does not matter, there's only 4 possibilities. And the same with the 6 students. If we systematically list off 3 letters where order is not relevant, we only get 20 different possibilities there. And of course, that's a lot more than the 4 teachers because we have more students to pick from than we do teachers. So I think if you can see all those, little groupings there in front of you, it probably makes sense why the fundamental counting principle has to be applied, because if you think of selecting maybe the teacher WXY group, then that WXY can be paired up with any one of those 20 student subgroups. The same with the WXZ second teacher group has 20 different options, and WYZ has 20 options, and yes, XYZ has 20 options. So that's why we need to say 4 choose 3 multiplied by 6 choose 3. And incidentally here, as we wrap up, it's just an interesting feature of counting problems is that sometimes you get a deja vu sensation, and you probably have it in this problem because this is actually the same kind of a counting question as the previous grid problems we looked at. And I set it up so it actually mimic the numbers exactly. So if we're trying to get from A to B and then to stop at B and then finish off by getting to C, we know we have to count the number of paths to get from A to B. And we also know we have to count the number of paths to get from B to C. And of course, there's 4 steps involved in the blue section here. We can choose either 1 or 3. So I'm just going to go 4 choose 3. And that's choosing exactly 3 north steps and a total of 4 steps. Again, where order is not relevant in the grid problem. And then from B to C, there's 6 steps. And we can choose either those 3 eastern steps or those 3 northern steps out of those 6, again where order is not relevant. And you're probably very comfortable with understanding that those 2 combinations have to be multiplied to determine your total number of paths from A to C, because the paths from A to B can continue to flow into any one of those 20 paths that will go through the pink section of our grid here. And it's the same thing with the committee problem, is once you choose your 3 teachers, there's 20 different possible student subgroups that can get paired up with any one of those 4 teacher subgroups, and that's why the fundamental counting principle is required to get our correct answer of 80 possible committees.